Hello again. So, students, we are here again for very small time because in last lecture, what we had a discussion about amplifier design. What happened? The screen is okay. Am I visible? The screen is visible. Yes, it's done. And see, we had analysis in last few lectures. We had analysis of a common emitter amplifier. Is it? And in this analysis, we started with some assumptions also. Is it is an h parameter module, then approximate h parameter module, then we had a discussion about what will happen if I want to design a practical amplifier, then what assumptions would be there. That's what all discussion we had. And now what I left with actual amplifier design. Is it? So today I am conducting this small session on design of amplifier. Is it? Intentionally I came here just to solve one numerical. Right. Only one numerical we will solve in 10 minutes and then we'll leave the class. So let us start with, instead of talking on the same analysis and design again and again, let us start with the design. What kind of design statement is there for CE amplifier, that I'm going to write here. So let me write the question. Here. Yes, that's what the question I'm writing. If you have pen and paper, if you have notebook, then please note, because see, I'm not going to write the full sentence here. I will dictate the design problem, you have to write it. I will just write few given things. For example, the statement is design. See, the statement is design single stage common emitter RC coupled amplifier for following specifications. That kind of statements generally are there. Design a single stage RC coupled amplifier or single stage common emitter RC coupled amplifier for following specifications, and they define specifications, they give specifications. Is it? So what are the specifications, or what are the given data? Sorry, the given data is, those are the given data. First thing, they have given as output voltage VO, which is equals to 3 volt RMS. See, initially they created a problem. It is RMS voltage they have specified. We know that RMS is different value from the peak voltage. So peak and RMS are different values, is it? So don't get confused, as they have not given the peak value, they have given RMS value. We have to convert RMS into peak value, is it? So whatever it is, we'll follow the process afterwards, but for the time being, let us start with the given data. Is it? Now the given data, the second thing is gain, that is voltage gain they have given. So voltage gain is 20. Obviously it should not have any unit, so given data V AV, instead it is 20. Then they have specified frequency range. Frequency range they have given 20 Hertz to 20 kilohertz. Yes. Then they have given stability factor for amplifier, it is 10. Then they have specified BJT beta, which is 330. Almost everything is given. Then they have given HIE. Now it is okay. It is 4.5 K instead K ohm. Okay, see, almost everything is given. Now what is my job? My job is to design single stage common emitter amplifier for those specifications. Is it? By using those given data, we have to design amplifier. So as if we want to design amplifier, let us start with the circuit diagram. The first thing generally we do is draw an circuit diagram. This is the first step always. Even if you want to write, you can write as step 1, and in any electronic circuit design, the step 1 is draw the circuit diagram. Is it? So let me draw the circuit diagram. Now look at here. This is the base, and now one resistor, what we call it as R1, is connected, R2 is also connected, this is C in, and somewhere here it is input voltage, source voltage V in. Here I am connecting or ground terminal, this is output voltage, here I am taking, this is VCC, I'll write plus VCC, one capacitor. We had discussion about this capacitor, it is bypass capacitor, call it as CE, call it as R1, R2, C in, C out, and this is RC. Okay, let me call it as RE, and this is transistor Q or T, whatever it is. See, all done? Yeah, this is what the circuit diagram. Now, the first step is always drawing a circuit diagram. Is it step number 1 is draw circuit diagram. Now, step number 2. It's on us. I have to decide which is step number 1, which is step number 2. But see, generally, whenever you want to start with the circuit design, you have to draw the circuit diagram first. Is it? Now, things are given, output voltage is given, gain is given. The only and the most important thing that drives the amplifier is VCC, the supply voltage, which is not given. So that I need to calculate first. So let me write the second step as calculation for VCC or calculation of VCC. Now see, for better operation of this circuit, was it that VCC, for better operation, always to settle the Q point exactly at the center, that VCC should be always greater than or equals to twice of VO peak to peak. See, this is not a mandatory condition, but if you have this, then it is always better. See, I am not saying this is always mandatory, but see, if you keep the VCC greater than twice of output voltage, twice of peak to peak output voltage, then your circuit will work properly. Your Q point will stabilize properly. The Q point will settle exactly at the center, not exactly, but about at the center. Is it? So that's why this condition generally people follow. Is it? This is the best assumption, the best consideration, what I can say. Okay, if I go with this consideration, then what will happen? Let me write down here. First, VO peak to peak. See, this what is VO peak to peak? It is given? No, it is not given. So if you calculate V peak, V peak means what? VM generally. Then it is okay that V peak to peak is nothing but twice of V peak. Is it? So this is a common thing. Peak to peak means what? Twice of peak. But what about V peak? That is VM. It is not given, na? So V peak, or what I can say VM, is nothing but your do you remember that? See, okay, VRMS, pen change किया ना मैंने, VRMS, yes, VRMS is equals to VM by root 2. ये तो पता है हमें, we know, सगळ्यांना माहिती आहे VM divided by 2. Then what is that VM? Then VM will be obviously equals to VRMS multiplied by root 2. So can I have this V peak, that is VM, is equals to VRMS multiplied by root 2. But what is that VRMS? It is 3. It is given, na? VRMS, look at this. VRMS is given. Multiply by root 2. That's about 3 root 2. So 3 multiplied by root 2. How much it will be? Oh, sorry. Let me take calculator. I hope you all are using this calculator, FX8 to MS something. I'll use it. Now this is what V peak. So V peak is equals to 3 root 2. Then what about V peak to peak then? V peak to peak will be twice of 3 root 2, is it not? Yes, is it not? So let me calculate V peak to peak directly. So V peak to peak will be twice of 3 root 2, means it will be 2 multiplied by 3 root 2 is equals to, let me calculate this, 3 root 2 multiply, sorry, 2, 8.48. So it will be 8.48. So this is what my V peak. But my aim is to calculate VCC, not V peak to peak, is it? What is VCC? VCC is generally greater than or equals to twice of V peak to peak. It means that VCC can be equals to twice of 8.4. So I will write 8.48. So 2 multiplied by 8.48. It means VCC can be greater than or equals to about 8 to 16.5, about 16. I can write about 16. Yes. See, every time I am writing approximate value. If you have calculator, then you can do the calculation. That 8.84 multiplied by 2, you are getting 17.68. I have written 16, no problem. Even even if you assume, see, even if you assume a VCC is equals to 15 volt for a sake of your calculation, then also it is okay. If someone assumes VCC is equals to 16, it is also okay. If someone says VCC is equals to 17 volt, then also it is okay. It's on us, is it? So approximate or the standard consideration says VCC should be greater than or equals to twice VO peak to peak. So the value of VCC should be about or around twice of V peak to peak, is it? So twice of V peak to peak is 17 volt. So if it is exact 17, then plus 2 minus 2, it is tolerable. So plus 2 means you can go up to 19 volt, minus 2 means you can go up to 15 volt, no problem, is it? Even if you assume 14.5 or 14, then also it is okay, but for good sake we'll assume VCC is equals to 15. That's all. So we can go ahead with this value, is it? I told you, you can go ahead with this or this also, no problem at all, is it? I told you at the design, you are the designer, it's all on you only, is it? Whatever you decide is the final thing. That's what. So now I have decided VCC is equals to 15 volt, I will go with 15 volt. Do one thing, you assume VCC is 16 volt, you go with your values, is it? So finally what we are doing, we are calculating all the value of resistors and capacitors, is it? So if I take VCC 15, you take VCC 16, your values, rest of the values for all those components will be different from my values, and those will be slightly different, is it? For example, from this VCC, if I am taking VCC is between, my value of R1 and R2 will be different, maybe your value of R1 and R2 will be different, maybe his value of R1 and R2 will be different. Obviously, because R1 and R2 divides VCC in two parts. We know that because R1 and R2 form a voltage divider network. So obviously VCC will get divided into two parts with the help of R1 and R2. So that's why those R1 and R2 is dividing VCC, and now I have assumed a different VCC. I have 15, you have 16, one of your classmates maybe he is having 17 volt VCC. So my value of R1 R2 will be different, your value of R1 R2 is different, and your classmate who has assumed 17 VCC has a different value of R1 and R2. Now which one is correct, is it? If you have designed it and if you give me your assignment or your state design problem to check, then I will say this is right, this is also right, and this is also right. I will not check the values of R1 and R2. What I will check the proportion of R1 and R2. Is it? The proportion. No matter what is the value of R1 and what is the value of R2, I will check the proportion. For example, if value of R1 in my case if it is 1 kilo and R2 is 5k, I'll say it is okay. Alright, wait. The value of R1 has to be large, na? So while assuming something, assume the right data. So value of R1, if it is 5k and if this is 1k, I'll say this is okay. In one case, for VCC is equals to 15, I am getting 5 and 1. In case of VCC is equals to 16, maybe I am getting this value about 20k and this value is about 4k. I'll say this is also okay. Yes, it can be. In one case, maybe in another, I am getting this value is equals to 15k and maybe this value is about 3k only. I'll say this is also okay. See, values are completely different, 5k, 20k, 15k, but still all values are correct, because what is my checking is value of R1 should be greater than or equals to minimum twice of value of R2. That's what I check generally. Every designer has to maintain that proportion. Value of R1 should be large than R2, and how much large? At least it should be greater than or equals to twice of R2. Is it? जो कुछ भी R2 का वैल्यू होता है उसके डबल से ज्यादा होना चाहिए. That's what. So 1k का डबल होता है 2k and it is greater than 2k. It is valid. Now this is 4k का डबल होता है 8k and this value is greater than 8k. It is valid. So 3 डबल होता है 6k. It is 15k which is greater than 6k. This value is correct. So no matter what the value you have calculated, if you are the designer, the matter is proportion. Is it? So that's why I'm telling you that VCC is equals to 15, 16, 17, no matter what's the value you have assumed, because we are the designer, we are free to assume any value. Even in your question paper, the note which is written is assume suitable value. See, assume, and the most important word is suitable. Assume suitable value. Every question paper of your designing ACD1 or ACD2, they have written a word assume suitable value. So what is that value? This word is really important. You just need to select any suitable value. Is it? Select VCC 15, 20, whatever value. The proportion of the component has to be correct. So your amplifier will work with R1, R2, 5, 1k, no problem. Your amplifier will definitely work properly for R1 is equals to 20k, R2 is equals to 4k. Also your amplifier will work fine for R1 is equals to 15k and R2 is equals to 3k. Is it? Got the point finally? Because value doesn't matter, the proportion of value matters. Is it? So this is about selection of ACC. See, amplifier circuit diagram is there. We have calculated VCC. Now step by step, go ahead. Third point. Now third step is, now as we know VCC, my job is to find out what is the Q point voltage and current. Is it? So if it is now Q point, find out Q point voltage VCQ. And it is known VCQ. If I want to set the Q point exactly at the center of the DC load line, then I must have this VCEQ is equals to VCC by 2. Now VCC you have assumed, I got 15, then it is 2. It means for my case VCEQ is equals to 7.5 volt. That's what it is. Isn't it so simple? Now the fourth step is, see, whatever assumptions I made, based on that assumptions I am going to proceed. Next calculation is, I will calculate the value of voltage across emitter resistor R. That value I have to assume. Let's see, you if you focus on the circuit diagram, what I am going to do, see, I am just clearing this output part. See, this part is done, VCQ I have calculated, and now I'm interested in voltage across RE. Look at this. This is VRE. This is VCQ. Is it? And for this, what I need? I need VCC, some part of VCC. Is it? So basically, focusing on the output part. What I need for output? VCC is needed, VCQ is needed, VRE is needed. So that's what I started, and now it's time for VRE. Now VRE, assume VRE is 10 to 15% of VCC. Now that's the thing. VRE is equals to 10 to 15% of VCC. Now see, one can assume VRE is 10% of VCC. Another student can assume it is 12% of VCC. One can assume 14% of VCC, and another can assume 15% of VCC. All values are correct. What I told you, that value doesn't matter, the proportion matters. Now you go with 10, 12, 11, 12, 13, 14, 15, whatever. It is a rough assumption for voltage across RE. Now what I will go with, I'll go with VRE is 15% of VCC. So if it is 15%, it means 0.15 multiplied by, what is it assume? Yes, it is 15. So 15 multiplied by 15. I'll calculate 0.15 multiplied by, if it is 15, then 2.25 is the value. Don't forget to this. I have VRE is equals to 2.25 volt. Is it? So if you're going with VRE is 14%, then you must write 0.14. If you are assuming 12% of VCC, you have to write 12%, that is 0.12. Is it? It's on you only. Whatever you have assumed, go with your assumption and calculate the values. Is it? So now till now, what we have calculated? VCC, Q point we have calculated, VRE we have calculated. Is it? And we focused on the output part of the circuit. As we have focused on the output part, let us continue with the output part. Now, in what's the number? It is 4th or 5th? Let me check. It is 5th, I think. Yes, 5th. I will calculate RC calculation for collector resistor. See, what is that? RC is collector resistor. Now related to RC, do we have any equation related to RC? Now see, H module, approximate H module analysis. From approximate H module analysis, we have this equation: AV is equals to HV multiplied by RC in parallel with divided by HIE. If you don't remember that, let me scroll down, and yes, let me show you the summary. Look at this. Voltage gain is equals to, you remember that, it is HFE RC in parallel with RL and divided by HIE. But now in this case, we don't have any RL. Do we have RL, load resistor? No, we don't have any RL. So if RL is not present, okay, let me mention it. If load resistor RL is not there, then AV becomes, AV, it becomes HFE multiplied by RC divided by HIE. Now see, voltage gain is given. Look at the data. Voltage gain, where is voltage gain? Voltage gain is given. See, this AV is given, beta, that is nothing but your HFE is given, HIE is given. Well, what is it? Beta, this is what your HFE. sorry. It takes some time to settle. Okay, let me plug out the internet. Now what is this? This is HFE. Now see, HFE is known, AV is known, HIE is known. So it means I can calculate value of RC. Now what is that RC? RC is equals to AV multiplied by HIE divided by HFE. I just simplified the equation. Now what is that AV? AV is 20. What is that HIE? 4.5 kilo ohm. What is that HFE? HFE is 330. Yes, it is 330. Just check. Yes, it is 330. It is 330. Now use your calculator and then calculate the value of RC, that is collector resistance. 330K, the value comes around 272.3.72 ohm. See, we are calculating the value of resistor, so it must be ohm. Don't forget the unit, and this is what your collector resistor. This is what my collector resistor is. It 272.72. So at the time of a practical, you select RC is equals to 280 ohm. See, if you go to the market and ask shopkeeper to give you the value of 272.72 ohm, obviously he will not give, he will refuse. Why? Because whatever value you have calculated are not available in the market. And why it is not available, I explained it in the first lecture of this semester in tolerances of resistors. Is it matters, and that's why we have to select a nearby values instead of the exact value. So exact value is 272 ohm, which is not available in the market. So whatever nearby value, may be upside or downside, whatever is available, we have to select. So 280 ohm is available, take 280. If 270 is available, take 270. No matter what's the value, but it should be in the nearby value. Isn't it? Everything is approximate, I told you. Now see, one value we have selected from the output side is RC. Now see, the Q point first we have selected, and only VCQ we have calculated. We have not calculated ICQ. So now let us calculate value of ICQ. The number is 6, I think, and then I'll write calculation for ICQ. How you will calculate ICQ? Apply KVL to output loop. And then equation becomes VCC is equal to IC RC plus VCEQ and plus VRE. Now you will come to know why I have calculated VCEQ and VRE immediately when I start with the circuit diagram. See, first we started with the circuit diagram, then I have calculated VCQ and immediately I have assumed VRE because I know that somewhere I am going to use this VRE. Is it? Now VRE is known, VCQ is known, RC already we have calculated 272 around, and VCC is known thing. So IC, this IC is nothing but my ICQ. Don't forget that this is what my ICQ. So value of ICQ will be, look at this, VCC minus VCEQ minus VRE divided by RC. Yes, it is. VCC is 15, VCEQ, how much VCEQ? Yes, it is 7.5 minus VRE. What's the value of VRE we have calculated? Yes, 2.25. Let me check the value 2.25, whether it is 2.25. Yes, it is 2.25. Divided by value of RC. RC is 272.72. And calculate ICQ with the calculator. Then what I'm getting around 19.3 milliamperes. What I'm getting actually on my calculator, 19.3 into 10 raised to minus 3. So 10 raised to minus 3 means around 20 milliampere. We can say approximately 20 is the value of ICQ. Yes, this thing is done. We have calculated ICQ. See, we are still in output part. Is that we have calculated VCQ, ICQ, RC. We are still in output part. Now, as if we are considering only output part, what else is there in the output part? Look at the output arm completely. We have another register called RE. So for any value of register, what we need to get the value of register? We need voltage across the register and the current flowing through that register. Now see, value of RE will be equals to VRE divided by IE. Voltage across RE and current flowing through RE. Now this value of IE, this is approximately nothing but IC. In my case, it is ICQ. C is approximately I. So this is IE. IC is approximately IE. So it means IE is nothing but your ICQ in my case. So ICQ is nothing but IE. So I will put ICQ instead of RE. So it will be 2.25, which is value of VRE, multiplied by ICQ, that is 19 point, what's the number? 19.3 milliamperes. 3 milliamperes means minus. Then value of RE will be let me take calculator. 2.25 divided by 19.3 milliamperes. Some error. 2.25 divided by 19.3, 116. So it is 116.5 ohm. 116 ohm is the value of emitter resistor. Is it? So practically you can select 100 ohm. If 120 ohm is available, then also you can go for 120 ohm. If it is available, then go ahead. Otherwise, select 100, majorly always available. So those are the values of RE that we need to select. Good. So 116.5 is the calculated value. Practically, whichever value is available in lab, we have to take it. It is 100 or 120. Which one is available in the lab or in the market? Go ahead with the value. Your output voltage will not exactly, but will be about or around the desired one. So see, if you are simulating that circuit, then also you can use 116.5, because it's a simulation. If it is a protest simulator or any simulator, you can put exact values, no problem. Practically we have to use different values, is it? Because physically we don't need to put any value in the protest can handle any value. उधर का physical value देना नहीं पड़ता. So that's why it is okay with protest. But if it is a lab, approximate values or available values must be there. So now see RC, RE, two registers from the output side we have calculated. VCQ, RE, VRE, those are known. Even ICQ we have calculated. So output part almost we are done with. Now come to the input parts. What is there in the input? We have two registers. Those are biasing registers. You remember that is step number, I forgot, step number 8. It is always good to write your step numbers. Now from the input side we will write cal for biasing resistors. Calculation for biasing is R1 and R2. Yes, that's what it is. Now, related to R1 and R2, one thing I know is R1 in parallel with R2 is nothing but your generally the parallel combination of them is nothing but your RB, and this RB is here in this equation of stability factor. So you know stability factor, it is 1 plus beta. I hope you remember the equation, divided by 1 plus beta RE divided by RB plus RE. This is what equation, right? Reference, it is a stability factor equation, voltage divide studied. So from that, voltage divider by circuit is the most popular circuit for the amplifiers, and from that voltage divider by circuit we have taken stability factor equation. So stability factor shows this equation. Let me check whether all is going okay. Everything is fine. Now where's the pen? So this is stability factor equation. Now what is that beta? Beta is nothing but your HFE. Yes, all set now, because see beta, what is that beta? This is HFE. It is how much it is given? It is 10. HFE, how much it is? It is 330, I think. It is 330. What's the value of RE you have calculated? It is 116.5 ohm. What else is there? Beta RE. Now from that we can calculate value of RB. See, almost everything is given from the equation. Only one value that we need to calculate. So let us calculate the value of RB. Is it use your calculator, put all those values. Stability factor is equals to 10, beta is equals to HFE, that is 330, RE is 116. Then stab RB. Let me write value of RB is 1.08 kilo ohm. This is what my value of resistor RB is it. But what is that RB? You remember that RB is nothing but your, see, I have calculated RB from the stability factor equation. That RB is nothing but your R1 in parallel with R2. It means R1 combination. So R1 R2 divided by R1 plus R2. That's what the actual value is it, which is nothing but 1.08 kilo ohm. Come to the part of interest. The part of interest is this. R1 multiplied by R2. Can I rewrite this part? Let me rewrite this as R2 by R1. Okay, forgot plus R2 multiplied by R1 is equals to not 8 kilo. See, intentionally I am using a different pen because I want to highlight that. Somewhere I am going to use that. Is it somewhere? Now come to the next part. Next part is we will calculate the voltage across R2, because finally I am interested in R1 and R2. So there is no way to calculate R1 and R2. So I have calculated parallel combination of R1 and R2. Was it parallel combination of R1 and R2? I got the value RB, that is 1.08 kilo ohm. Is it? Now from the voltage divider by circuit, voltage across R2, is it voltage across R2? Okay, let me write it as VR2. Now, what is that VR2? From the voltage division rule, VR2 is nothing but, look at this, R2 divided by R1 plus R2 multiply by VCC. The voltage division rule, look at this. This is R1, this is R2, this is ground. I am interested in voltage across R2. I am interested in this voltage. Look at this. This is R2, this is R1, and this is VCC. Then what will be the value of VR2? You have studied this in network. It must be R2 divided by R2 divided by R1 plus R2 multiply by VCC. That's what the equation you write generally in your network analysis. So I did the same thing. Look at this. I did the same thing here. Voltage across R2. So is there any other way to write down the value of R2? Yes, I have the way. But before that, let me simplify this equation. It is VR2 divided by VCC, which is equal to R2 divided by R1 plus R2. That's what this VCC comes on left hand side. So it's a ratio now. What I'm getting is a ratio. Okay, now apart from that, see, only VCC is known. Out of this 4 term, that is VR2, VCC, R1, R2, only VCC is the only term known. So obviously, by knowing only one term, we can't proceed. What I need is one extra term. So it means now, is there any other way to calculate value of VR2? That's what I need to hunt for. Now, let me write VR2 is also given by. Now, look at this. VR2 is also given by VR2 is also given by what? Yes. Now here we need to focus. This only concentrate on this diagram. We are interested in voltage across R2. Look at this. That's what my interest. Let me use another pen. That is what my what happened. This is VR2. Is that the voltage across resistor R2? Now look at this. Voltage across resistor R2 is nothing but this voltage plus this voltage. Now what is this voltage? Look at this. What is this voltage? And what is this voltage? This voltage is the base to emitter voltage. And what this? This is voltage across resistor RE. So I can clearly write it is VRE. So VR2 from the diagram, it can be written as VBE plus VRE. Now what's the value of VBE? The transistor in the amplifier is always in active region. So if the transistor is in active region, the value of VBE will be 0.7 volt if I'm using silicon transistor. That is most important. If you are using germanium transistor, then go with 0.3. But now I have silicon transistor, so that's why I'm writing 0.7. And value of VRE is 2.25. 2.25 already calculated. So value of VR2 will become it is 2.25 plus 0.7. It means it is 2.95. This is value of 2. Now this value I am going to use in this equation particularly. Look at this value of VR2. Look at this. Put this value of VR2 directly in this equation. Then what you will get? You will get 2.95 divided by VCC equals to R2 divided by R1 plus R2. Now what is value of VCC? VCC is 15. So R2 divided by R1 plus R2. 2.95 divided by 15 is, go for calculation, it is 0.19. So from that what I can write? I can write R2 divided by is equals to 0.9. Now look at this, I got this factor. Now this factor I am going to use in this equation. Now look at this, let me copy this equation. Okay, just write the equation instead of copying that. What happened? Is all okay? Whether it is writing? Okay, it's a black one. No problem. R2 divided by R1 plus R2 is equals to 0.90. Now, where we have seen this R2 divided by R1 plus R2 is equals to 0.19. Where I need to put this value here in this equation. Let me highlight it. This equation. Is it? Or let me search for, is there any other? Yes, I can use this ratio here. Now look at this, R2 divided by R1 plus R2 multiplied by R1 is equals to 1.08. See, things are simple now if I use this equation. Is it? Now let me rewrite the equation. It is R2 divided by R1 multiplied by R1 is equals to it is equals to 1.08 kilo ohm. This is what the equation. Look at this highlighted thing. Let me delete the second highlighted. Now look at the highlighted. Now it's R2 divided by R1 plus R2 multiplied by R1 is 1.08 k. That's what I have written. Is it? Now put this value of R2. Oh, what happened? What happened? What happened? Yes, it's working. R2 divided by R1 plus R2 here. It means now what the factor I can write it 0.19 is equals to 1.08 kilo ohm. Is it? So value of R1 will be 1.08 kilo ohm. It becomes double by 0.19. So it means value of R1, if I use my calculator instead of brain, then I can calculate the value of R1 is around 5.68 kilo ohm. Yes, it is 5.68 k is the value of R1. Now is it what we need always? No, we need a pair of R1 as well as R2. So only R1 is not sufficient. From that, can we calculate R2? Yes, if we know the combination of R1 and R2, multiply by R2, or what I can say, R1 plus R2. If I know this thing, that is 1.08 kilo ohm, and if I know value of R1 is 5.68 kilo, then it is possible for me to calculate the value of R2. Is it? So let's go for it. Calculate value of R2, and by putting the value of R1, that is 5.6, then easily calculate R2 is equals to, use your calculator, I got the value 908.12. Value of R1 I have calculated is 5.68, and value of R2 I have calculated is 908.12 k. I told you, if you are using protist, then go for the actual values. If you are doing the experiment in lab, then nearby values I can use 5.6. Yes, 5.6 is available. Even 5.5K is also available. Go for these values. Now here 9089, or we can say 1 kilo ohm. Yes, 1 kilo ohm is the best suitable value. Go for this value only. Even I am not going to suggest the another value. So 1K is okay. Go with 1 kilo ohm value. So those are the values for R1 and R2. Let's look at this. R1 and R2 we have selected. Now this is done. See what else is there in the diagram? All the values of resistors we have calculated. Okay, and it's not about only resistors. See, we have calculated RC, RE, R1 and R2. Now, the important thing is we have to calculate capacitors also. Let's start with the calculation of capacitors. Calculation of capacitors. Now, which capacitor do we need to calculate first? Let's go for it. First is the bypass capacitor. See, coupling capacitor and bypass capacitor. Only two capacitors are there with us. In case of coupling capacitor, again we have input coupling capacitor, output coupling capacitor, and then we have to calculate bypass capacitor. Is it? If you want to, you can calculate separate input and output coupling. Otherwise, just calculate coupling capacitor by considering the input impedance. That's what it is. But still, as we have time, we'll go for C in and C out separately, and then we'll calculate bypass also. So first, let us start with bypass capacitor CE. Now, to calculate bypass capacitor, what I told you, what's the assumption? It is XCE is 10% of RE. That is the thing we need to assume. In last lecture, we had a discussion about that. Is it? So now, what is the value of RE? RE is 116. So value of XCE, that is 10% of 116, is 1.16. Is it not? This is value of XCE. Now XCE is 1.16. It is okay. Let me rub it. What happened? It's not. It's stuck. So wait. Now things are okay. We need a pen. Value of XCE is 10% of RE. That's what. Check what's the value of RE. It is 116. So if it is 116, 10% of 116 is 11.6. 11.6. So okay, right now ohm as. So 11.6 ohm is the value of XCE. What is the equation for XCE? It is 1 by 2 pi F CE. Now what is that F? It is 20 Hertz, because I told you that it's a lower cutoff frequency, that is FL, which is given in the design statement. Okay. Now see, put the values. Put XCE is equals to 11.6. Put F is equals to 20 Hertz. Put the value of 2 pi and then calculate CE. Use a calculator. And if I go for the equation and the values, then a value of CE that I get is around 683.4 multiplied by 10 raised to minus 6. That's what something. This figure is displayed on your calculator. So it means, see, 10 raised to minus 6 means micro. So I will write 683.4 microfarad. Microfarad. So the value of bypass capacitor, the exact value of bypass capacitor or the calculated value is 683.4 microfarad. So 683 is available in the market. No. So the best thing is to use 1000 microfarad value of a capacitor for CE. Go for it, no problem. Because if you search for a value which is less than 683 in the market, then directly you will get 330 or 440. So instead of using less value for bypass capacitor, it is always good to have large value than whatever you have calculated. So 683 around 700 is the value you have calculated. The larger value in the market available is direct 1000 microfarad. So go for it. Is it? So this is what CE. The same way or same methodology can be applied to calculate value of C in, that is input coupling capacitor. Now for C in, this X C in of R in. So here to calculate C, calculate in first. R in, R in is want exact value, then go for n is equals to HI. No problem. Both values are okay with us. Is it? So if you calculate exact value, that is R in is RB in parallel with HI. RB is known. Value of RB, it is 1.08 kilo ohm, which is in parallel with 4.5. So that's why in my case value of RB is less than your value of X in will be small. So you can go with this R in. Now if I calculate, okay, if I consider RB and HIE, and if I calculate value of R in, then value of XC in will be okay, first we'll calculate R in. R in will be and X is 87 multiplied by 87. Then calculate C in, and the value of C in that you calculate after all this process is around 91.1. Is 100 microfarad. Go with 100 microfarad. See, if you calculate Rn by this value, then also it is okay. I told you that value doesn't matter, the proportion matters in designing. Is it? So that's why value of C in and C out. Okay, still C out calculation is pending. Let me finish it in 2 minutes. Value of C out, that is output coupling capacitor, which is the last part of the C out, a same 10% of value of RO by value of RO is what is RL. Actually, the only RC. Now, what is that RC value you have calculated? It is 272.72. Is it? So, X out is equals to 10% of 10 ohm. Is it? Then go ahead, Xc out is equals to, again following that C, and the process already use the calculator efficiently. Then C out will be 284 point something microfarad. So 230. See, we have, is it? If components already we have calculated, what else is there in the circuit? Just check, just check, just check. Oh, we forgot the main main character from the circuit, that is transistor. So selection of transistor is not a big deal because everything is given. Let me copy that, whatever given, it is given. Now it's not happening. Done. Take some time. We have to select the transistor. How to select the transistor? If you have HFE and HIE, even if you have only HFE data, you can go for the selection of transistor, because in case of amplifier, what we badly need is HFE. That's what, because we never deal with what is the maximum value of ICQ and all those things. We need HFE. See, I had a different session on datasheet of transistors. So you will come to know selection of transistors very well there. Now let me copy the same thing here. Come on, come on, come on. Paste. Now look at this. This thing is nothing but my HFE. Thing is nothing but my HIE. Now this HFE and HIE matches with the 5 BC547, which is general purpose transistor commonly electronics lab. So we'll go for that transistor and we'll implement the circuit on breadboard and we'll check the results. Even if you are doing the design in protest, then also you can work with BC547. It is completely feasible. HFE, HI values are matched, and if you don't understand selection of transistor, then go and watch that selection of transistor video, or what I can say, the title is data sheet or specification sheet for a transistor. Is it? So you will come to know almost everything about the selection of transistor by that way. So this is what all done about the transistor common emitter single stage RC coupled amplifier design. I'll share you that PDF also, whatever process we have done here. I'll share the PDF also, so you will get some kind of written notes as such. And this is all about the design of single stage RC coupled amplifier. In next lecture, I'll provide some extra numericals related to the same transistor amplifier. Okay, thanks a lot.